Let's talk a little bit about the impulse response of a system, what it means, and why we care about the impulse response of a linear time invariant system. As the name suggests, the impulse response of a system is just the response of the system to a input which is the unit impulse. So let us say we have a system H, and let's say we first consider a discrete time system. So we have a system H, and if I input a certain signal into this system, I'm going to get a certain signal at the output of the system, right? So suppose we consider an input which is the unit impulse signal. So I consider an input which is just a signal which looks like this, which is non-zero just at time n equal to 0 and is 0 everywhere else. I'm going to get a certain output from the system, right? This can be thought of as the response of the system to the unit impulse input, and that is what we call as the impulse response of the system. So this is called, h of n is called the impulse response of the system. So let's take a quick example and then see how we can find the impulse response of a system. Okay, so maybe I will give an actual practical example. Suppose we have a system, or let's say we are trying to model a room with some echo as a system. Let us say we have a large room and somebody speaks into the room. So we have an input signal, say x of n, and we have a receiver sitting in the other end of the room. And so here is perhaps somebody who speaks, and here is a receiver. So this is more like a speaker here and a mic here. So you may have one path that directly reaches from the speaker to the mic, or it was what's called as a line of sight path. But you may also have a reflection from the wall, but the reflection may take a little longer to arrive, and there may be some attenuation because of the reflection from the wall. So let us say that this path takes 1 unit of time more than the direct path, and it has an attenuation of a half. So what that means is that the signal that your mic is actually going to pick up is not x of n, but it's actually x of n plus a half times x of n minus 1. Right? So now we have a mathematical model for what's going on in the room. Okay. Now, what is the impulse response of this system? Well, the impulse response of this system is simply the output when we set x of n to be equal to delta of n, which means that h of n is equal to delta of n plus half delta of n minus 1. Okay. So if I were to sketch this, I would get something like this. So this is the impulse response. But let us see whether it makes physical sense to think of this as the impulse response. Well, it kind of makes sense, because if you think about an input which is just a delta, and that's going through this room, so what happens is this: at time n equal to 0, an impulse is transmitted, and because there is this direct path, it is immediately received at the mic at time n equal to 0. But there is no reflected path at this time, because the previous input that was transmitted is 0. Okay. However, at the next time instant, what's going to happen is, because of this reflected path, the signal here, which had a amplitude of 1, would have taken one more unit to arrive at the receiver, and it would be attenuated by half, right? So the received signal would actually look like this, and that's exactly the same as the impulse response here. Okay. All right. So why do we care about the impulse response? What's so special about this? Well, it turns out that the impulse response completely characterizes a linear time invariant system. What I mean by that is that if the impulse response of a system is known, then we can find the output of the system for any arbitrary input x of n. Okay. So h of x of n is the output of the system for an input which is x of n. So it turns out we can compute this for any x of n if we knew the impulse response. Okay. So I'm going to try to explain why this is possible and what the exact relationship between the output and x of n and h of n is. Okay. So to do that, let's look at an example. Okay, so let's consider the following example. I have a system h whose impulse response is given here. Okay, so notice that this is a signal which starts at 0 and goes up to 3. Perhaps you can think of this as modeling a room where there are many there are 3 echo paths. But this may be a little bit confusing because it looks like the largest value is taken for a unit delay, so perhaps it's not the impulse response of that models an echo. Okay, but you get the idea. Now I have an input x of n which is given here. Okay, so what we would like to do is to find out what the output is. Now what we're really going to do is to take advantage of the fact that the system is a linear time invariant system. In fact, I need to tell you that the system is a linear time invariant system. Okay, otherwise what I'm going to say now is not going to make sense. So in this case, we knew that the system is linear time invariant, and we know that the impulse response is given in the figure here. Okay, so the key idea here is the following, is to think of the input as the sum of delayed impulse functions which are all weighted by different values. Okay, and then use the linearity and time invariance to compute y of n. Well, let me explain what I mean by that with this figure here. Okay, so this input is exactly the same input that I had before, x of n, and we want to find the output corresponding to this input. That's the problem we want to solve. Okay, so notice first that I can write this input x of n as the sum of 4 signals. Okay, look at the first signal. The first signal is non-zero only at -1. The second signal is non-zero only at 0. The third signal is non-zero only at 1. And the fourth signal is non-zero only at 2. And the height of these signals are all exactly the same as the values taken by x of n at these points. So now you would agree with me if I said that you can write x of n as the sum of these 4 signals. Right? Yeah, if it's not clear, stop the video here, think about it, see why the signal can be written as the sum of these 4 signals. Okay, now if you're convinced, let's move on. Notice that this signal here is actually can be written as x of 0 times delta of n. Now, what do I mean by that? Now, notice that it's clearly a signal that is non-zero only at n is equal to 0. So, this is clearly something like delta of n. It is just weighted by some number. Well, what is it really weighted by? Well, it's weighted by x of 0, because the value taken by this signal at 0, here, this value, is the same as this value. Okay. Similarly, this signal can be written as x of -1 times delta of n plus 1, because it's a shift of delta to the left by 1. This signal is x of 1 times delta of n minus 1. This is x of 2 times delta of n minus 2, so on and so forth. But in this case, we don't need any more. We need only 4 of these signals. In a more general case, we may need more than this. In fact, we will need as many signals as there are non-zero values in x of n. Right? Okay? All right. Now, how does this help in trying to find the output corresponding to the input x? All right, it helps because of the following. We know that the input delta of n results in this output. So if I were to multiply delta of n by x of 0, let's just look at this block here. Well, what this is really saying is this. If my input to the system were x of 0 times delta of n, because my system is linear, my output has to be x of 0 times h of n, because a linear system is homogeneous. Okay. Okay, so now it gets better. What about the output when the input is this? So here we're going to use linearity and time invariance. Now notice that the input here is just a shift of the impulse response impulse signal. The input is the impulse signal which is shifted and then multiplied by -1. So two things are going on. I take a signal which is the impulse signal. I shift it to the left by 1. I'm going to get something like this. And then I multiply this by -1, and then I'm going to end up with something like this. And that's exactly what this signal is. Okay. Well, but linearity and time invariance of the system tells me that the output should also be, well, what I mean by the output is, you can take the system, think of the input as being delta of n, and you will have a certain output. Now I can take that output, shift it to the left by 1, and multiply it by -1. And that ought to give me the output corresponding to this input. Okay, I think I made a small mistake. This is the no, that's right. That's right. I'm sorry, it's right. It's right. Okay, so this output can be computed, right? Because this has to be h of n plus 1, just h shifted to the left, and then just multiplied by whatever x of -1 is. So this is x of -1 times h of n plus 1. In the same way, we can see that this output has to be x of 1 times h of n minus 1, x of 2 times h of n minus 2. And now, because my system is linear, the overall output corresponding to an input of x of n is going to be the sum of all these outputs. We have to add all these things together. and that gives us exactly this. You may want to pause the video here for a minute and then make sure that you actually get this. Add these 4 signals and see that you get this. Okay? So this is why the impulse response is important. It lets you compute the output corresponding to any arbitrary input. So mathematically we can write this as follows. What we can do is we can say that any input signal, or any signal for that matter, can be written as linear combinations of shifted impulses. Can be written as follows, as let me use the same notation as in the book, which so Ax of k times delta of n minus k. For k going from minus infinity to plus infinity. Now I should mention something here, or point out something here. This x of n refers to a signal, whereas this x of k is the value taken by the signal x of n at time k. I think I mentioned this in one of my earlier lectures. We will be using x of k to kind of denote 2 things, right? So I mean, what it's essentially saying is the signal x of n can be written as a linear combination of weighted and shifted impulses. Okay? Now, because of linearity, what that means is this. The response of the system to x of n, which is y of n, is the sum of the responses of the system to weighted shifted impulses. What's the response of the system to delta of n minus k? That is h of n minus k. And what's the response of the system to x of k times delta of n minus k? It is x of k times h of n minus k. So this is finally what we are interested in. Because what it says is, it says, look, if you give me the function h of n and you give me the signal x of n, now we have a formula that says how we can compute y of n. Okay, this is called the convolution sum, or just the convolution of the signals x of n and h of n. So we write this as y of n is the convolution. Usually we use an asterisk to represent convolution. But it's very important to pay attention to the formula. The formula says it's x of k times h of n minus k. Okay.